I was 29 years old. I had just spent nearly 3 years building the atomic bomb, and I was about to stand in front of the greatest physicists alive and show them my drawings. Not equations. Drawings. Little stick figures. Squiggly lines on a chalkboard. Niels Bohr was in the audience. Paul Dirac. Robert Oppenheimer. The men who had invented quantum mechanics itself. And I was going to tell them I had found a better way to do physics, with pictures. Bohr stood up and told me I did not understand quantum mechanics. The audience gave up on me. My talk just fizzled out. It was the worst presentation of my life, and it led to everything that came after. Do not give up on your ideas just because the experts do not understand them yet. If you can see something true, trust your vision, even if you have to draw it. Let me tell you what happened. I have always thought in pictures, ever since I was a boy in Far Rockaway. When I looked at equations, I did not see symbols on a page. I saw colors, light tan J's, slightly violet bluish N's, dark brown X's flying around. I don't know why my brain works this way. It just does. When I think about electrons, I don't see mathematics. I see them moving through space, bouncing off each other, little particles dancing around, exchanging energy. My father taught me to think this way. He sold uniforms for a living. He was not a scientist, but he understood something important. When I was a boy, he would take me for walks. We would see something in nature, and he would not just tell me what it was called. He would ask me what it was doing, why it was doing that, what would happen next. Names are not understanding. Pictures are understanding. That is how I learned physics, not by memorizing formulas, by seeing what was really happening. At MIT, I was known as the kid who could solve problems nobody else could solve. Not because I was smarter, but because I could see them differently. Then came the war, Los Alamos, the bomb. We were trying to figure out if a nuclear chain reaction would work, how big the explosion would be, whether we would accidentally set the atmosphere on fire. When the war ended, I was exhausted. My wife Arlene had died of tuberculosis while I was at Los Alamos. I had watched the first atomic bomb explode in the New Mexico desert. I had seen what physics could do when it was turned into a weapon. I went back to teaching at Cornell University. I tried to do research, but nothing came. For 2 years, I was stuck, burned out. I wondered if I would ever have another good idea again. Then I started thinking about a problem that had bothered me since graduate school. Quantum electrodynamics, QED, the theory of how light and matter interact. It was supposed to be our best theory, the most precise theory in all of physics. But it was broken. Every time you tried to calculate something simple, like how an electron behaves, you got infinity as the answer. Infinity. Nonsense. The electron is sitting right there on your desk. It does not have infinite energy. But the equations said it did. Physicists had been struggling with this for 20 years. They had tricks to get around the infinities, ways of subtracting one infinity from another to get a sensible answer. But these tricks felt like cheating. I wanted to understand what was really happening, not just get the right answer. Understand it. So I went back to basics. I thought about what an electron actually does when it interacts with light. I drew pictures, little diagrams showing particles moving through space and time. An electron comes in here. It emits a photon. The photon travels over here. Another electron absorbs it. Simple pictures, like a child would draw. But when I translated these pictures into mathematics, something remarkable happened. The calculations became easy. Problems that had taken pages of algebra became one diagram on a napkin. I was excited. I thought I had found something important. I just needed to show it to the world. March 1948, the Pocono Manor Inn, a hotel in the mountains of Pennsylvania. 28 physicists gathered for a conference. Robert Oppenheimer had organized it. He invited the greatest minds in the world. Niels Bohr, who had invented the quantum theory of the atom. Paul Dirac, who had predicted the existence of antimatter, Eugene Wigner, John von Neumann, and two young physicists who claimed to have solved the infinity problem, Julian Schwinger, and me. Schwinger was my age, born the same year, 1918. But that is where the similarities ended. Schwinger was a prodigy from New York. He had published his first physics paper at 16. By the time of the conference, he was already a professor at Harvard. He dressed in perfect suits. He spoke in complete, polished sentences. He never used notes. He was considered the most brilliant young physicist in America. I was the kid who drew pictures. I had met Schwinger a few months earlier at another conference. I watched him give a presentation. It was like watching a symphony. Every equation flowed perfectly into the next. The audience sat in stunned silence. Schwinger had developed a complete mathematical framework to fix QED. His method was rigorous, traditional. It used the kind of abstract algebra that the old masters understood and respected. I had something different: pictures. The plan was simple. Schwinger would present his work in the morning. I would present mine in the afternoon. Two approaches to the same problem. Let the best theory win. Schwinger went first. He spoke for most of the day, without notes, without stopping. He filled blackboard after blackboard with dense mathematical equations, each one flowing perfectly into the next. His handwriting was immaculate. His logic was flawless. The audience watched in awe. This was how physics was supposed to be done, rigorous and beautiful. I sat in the back of the room, watching. My little pictures felt smaller and smaller with every hour that passed. When Schwinger finished, everyone applauded. Oppenheimer was beaming. Bohr nodded approvingly. This was the future of physics. This was how you fix quantum electrodynamics. Then it was my turn. I walked to the front of the room. I picked up the chalk. I started drawing. A straight line for an electron. A wavy line for a photon. Little arrows showing which direction time flows. I tried to explain what the pictures meant. An electron comes in from over here. It shoots out a photon. The photon travels through space and time. Another electron absorbs it over here. Immediately, hands went up. Paul Dirac interrupted me. Dirac was one of my heroes. He had written the equation that describes electrons. The Dirac equation, one of the most beautiful pieces of mathematics ever created. "Is this unitary?" he asked. It was a technical question about whether my mathematics was self-consistent. I tried to answer. I could see he was not satisfied. Then Edward Teller raised his hand. Teller would later become the father of the hydrogen bomb. He was not a man who held back his opinions. "What about the Pauli exclusion principle?" he demanded. "Can three electrons be in the same state in your diagrams?" I said yes. In my approach, you have to consider all possibilities and sum them up, even ones that seem impossible. The room grew restless. People were shifting in their seats. I could feel the skepticism building. Then Niels Bohr stood up. Bohr was 70 years old. He was the father of quantum mechanics. When I was a graduate student, he had come to a seminar where I presented my work, and he had laughed at one of my ideas. Laughed at it. Then later admitted I might be right, but this time, he was not laughing. He walked to the front of the room. He stood beside me. His voice was soft, that famous Danish accent that made everyone strain to hear. "You have drawn trajectories for electrons," he said. "But we learned 30 years ago that you cannot speak of electron trajectories. You are ignoring the uncertainty principle." He paused. "You do not understand quantum mechanics." The room was silent. Bohr continued lecturing me for several minutes about principles I had learned as an undergraduate, about mistakes he thought I was making. I stood there unable to respond, unable to explain. He did not understand. My diagrams were not literal pictures of electrons moving in straight lines. They were a shorthand, a notation, a way of organizing calculations, but I could not find the words to explain it. My ideas were too new. The language did not exist yet. The audience gave up. My talk just fizzled out. I walked out of that room a failure. That night, I could not sleep. Everything I had worked on for 2 years had just been dismissed by the greatest physicists alive. Schwinger was the hero. His mathematics was the future. My little pictures were a footnote. It got worse. When Oppenheimer returned to Princeton, A letter was waiting for him. From Japan. From a physicist named Tomonaga. Working in the rubble of post-war Tokyo, publishing on brown paper because that was all they had, Tomonaga had independently solved the same problem as Schwinger, using the same mathematical approach. Schwinger and Tomonaga, two great minds using the same method. The verdict seemed clear. I went back to Cornell. I was 30 years old. I had embarrassed myself in front of my heroes. Maybe I should give up this whole picture idea and learn to do physics the proper way. I almost quit, but something in me would not stop. I knew my diagrams worked. They gave the right answers, and they were simpler than Schwinger's pages of algebra. Calculations that filled 20 pages became one diagram. So I did what I always do when I am stuck. I went back to the physics, and I started writing. There was a young Englishman at Cornell named Freeman Dyson. He was 24 years old, just arrived from Cambridge, a brilliant mathematician. Dyson was curious about my strange diagrams. He would come to my office and ask questions. He listened carefully to everything I said. That summer, I was driving to Albuquerque to sort out a romantic situation that needed resolving. Dyson asked if he could come along. 4 days in a car, talking about physics. By the end of the trip, Dyson understood my approach better than almost anyone. Then Dyson went to Michigan for a summer school where Schwinger was lecturing. For 6 weeks, he listened to Schwinger explain his mathematical framework in detail. Dyson was now one of the only people in the world who understood both approaches, Schwinger's equations and my pictures. After the summer school, Dyson got on a Greyhound bus heading back to Princeton, 48 hours across America. Somewhere in Nebraska late at night, half asleep in his seat, something clicked. In a flash, Dyson saw it. My pictures and Schwinger's equations were not different theories. They were the same theory, seen from different angles. Every squiggly line corresponded to an equation. Every picture could be made rigorous. But here is what mattered. Dyson showed that my diagrams were not just equivalent to Schwinger's mathematics. They were better, simpler, and faster. A graduate student could learn my pictures in a week and start doing calculations that would take months using Schwinger's methods. Dyson published his paper in 1949. Slowly, attitudes began to change. Young physicists started using my diagrams. They found they could calculate things that had been impossibly difficult before. Problems that filled 20 pages of algebra became one picture. Schwinger's equations were correct, but within a few years, almost nobody used them anymore. They used my pictures instead. Schwinger noticed, and he did not like it. Years later, he would say, like the silicon chip, the Feynman diagram was bringing computation to the masses. He meant it as criticism. He thought physics should be elegant mathematics, not doodles. I took it as a compliment. My simple drawings had beaten his genius, not because they were more rigorous, but because they were more useful. If you are enjoying this story, consider subscribing. I tell stories like this every week about the real lives of legendary physicists. By the 1950s, my diagrams were everywhere. Every particle physics paper, every blackboard, and every physics department. The little pictures I had been laughed at for were now the language of modern physics. I think about that day at Pocono sometimes. I was standing in front of Niels Bohr, being told I did not understand the subject I had spent my life studying. My ideas were dismissed by the greatest minds in physics. It would have been so easy to give up, to learn Schwinger's methods, to do physics the way everyone else did it. But I could not. My brain does not work that way. I need to see things. I need pictures. Von Neumann once told me something I never forgot. He said, "You don't have to be responsible for the world that you're in." I interpreted that differently than he meant it. To me, it meant you do not have to think the way everyone else thinks. Von Neumann could calculate infinite series in his head. Schwinger could fill blackboards with equations that made professors weep. That was their gift. My gift was different. I could see around corners that they walked straight past. In 1965, I received a phone call at 4 a.m. I had won the Nobel Prize in physics, shared with Julian, Schwinger, and Tomonaga. The three approaches that Dyson had proven equivalent were finally recognized together. We shared the prize, but we did not share the legacy. Schwinger gave his Nobel lecture as a polished mathematical presentation. I talked about my mistakes, about falling in love with ideas before understanding their flaws. Today, Feynman diagrams are taught to every physics student in the world. Almost every calculation at the Large Hadron Collider starts with someone drawing my little pictures. Schwinger's methods are in the textbooks too. In the back. In the chapters that nobody reads. I was 29 years old, standing in front of Niels Bohr, watching my life's work dismissed as nonsense. 17 years later, I stood in Stockholm. The lesson? Do not give up on your ideas just because the experts do not understand them yet. If you can see something true, trust your vision, even if you have to draw it. If this story meant something to you, hit subscribe. I tell stories like this every week, about the real lives of the scientists who changed our world. These are the moments they do not teach you in textbooks.